Hello everyone, welcome to this lecture on statistical physics. Today we're going to consider the ideal Fermi gas. So we've looked at both gases and both Einstein condensates. So it's time to look at the other type of quantum distribution, which is the Fermi-Dirac distribution. And so to do so, we consider a gas of spin s fermions, which means that we will have a degeneracy factor of 2s plus 1, right? This is the number of spins along these spin components along the z that you can have for a spin s particle. So for example, for an electron, right, you can have spin up or spin down, so gs s is equal to 2. So what this means is the density of states, right? If we take the density of states, I call it DOF. If we take the density of states DOS of bosons times the degeneracy factor, then that will give us the density of states for free fermions, right? So if we take the density of states of free bosons and multiply it by this degeneracy factor, which accounts for the fact that you can have two electrons occupy the same energy state due to this degeneracy, then this will give you the density of states for free fermions. Okay, so in other words, the GE for fermions will be equal to GS V over 4 pi squared 2m over h bar squared to the 3/2 square root of E. Okay, note that we still have the same proportionality to the square root of the energy, so things are not too different from this point of view. However, things are different from the point of view of the occupation numbers because of the Pauli exclusion principle, right? I think we calculated earlier that the Fermi-Dirac statistics, in other words, the fact that for a given state the occupation can be either 0 or 1, implies that the average number of fermions can be calculated by taking the following sum over all of states, right? It's e to the beta e k minus mu plus 1. Okay, this we calculated earlier, and in most cases we are allowed to use the density of states. As long as we're not dealing with really low temperatures, we can approximate this as an integral. So for sufficiently non-low temperatures, then n is approximately equal to an integral of GE dE, this is our measure, over z to the minus 1, which is really this e to the beta minus mu, times e to the beta ek plus 1. Okay? And this is an integral over all of states. And we can do very similar things with the energy. So the energy is again a sum, and of course intuitively all we have to do is add here ek, and that will solve our problems. So a sum of e to the ek over e to the z minus 1 e to the beta ek plus 1, right? So this approximates to an integral which is GE dE over z to the minus 1 e to the minus e to the plus beta e plus 1. I think here I wrote ek, doesn't really matter because you're going to integrate over the variable. So, but for consistency, e. Finally, a last quantity that in the grand canonical ensemble is useful is the grand canonical potential. I'll write this as the pressure times the volume, right? So that's really minus the grand canonical potential. And what is this? Well, this is 1 over beta times the log of the partition function, but the partition function is a product, so this becomes a sum over k of log of 1 plus z to the minus 1 e to the beta ek, and again this becomes an integral, right? We couldn't do this density of states thing with the grand canonical partition function itself, because that is a product and you can't approximate a product with a sum or an integral. So this is 1 over beta integral of GE log of 1 plus z to the minus 1 e to the beta e dE. Right. So these are going to be the 3 main quantities that we will be interested in. And we can just plug in our density of states, which we found earlier. So let's do this, for example, with the number of, with the average number of fermions. So plugging in the density of states with the degeneracy factor, which we must take into account, that n is equal to approximately, but really who cares, equal to gs v over 4 pi squared 2m over h bar squared 3/2 integral of e to the 1/2 over z to the minus 1 e to the beta e plus 1 dE, and the energy goes from 0 to infinity because it's a free particle. Great. I'll do a substitution because I want the exponential to just be e to the x, right? Just as in the boson case, in the Bose-Einstein distribution. So I let x be equal to beta e, so dx is equal to beta dE. So this dE brings me a 1 over beta, and this e to the 1/2 brings me a 1 over beta square root of 1 over beta. So this is equal to gs times v over 4 pi squared 2m over h bar squared 3/2 1 over e to the power of 3/2 integral from 0 to infinity x over z to the minus 1 e to the x plus 1 dx. And now I think you should vaguely recognize this integral, because this is not too far off from the integrals we encountered when discussing the Bose-Einstein distribution, right? The main difference is we have a minus here, right? That's the only difference, actually. And so we are interested in these types of functions, and again, we can give them a name. We can give a name to these families of integrals, and I'm going to consider a more general case, right? So these integrals, I will evaluate them. So I define the Fermi-Dirac function, which sometimes gets confused with the delta function, but no, they're different things. 1 over gamma n, recall this, we had it before with the Bose-Einstein functions as well. Integral from 0 to infinity, x to the n minus 1 dx over e z to the minus 1 e to the power of x plus 1. Okay. So I will write this as 1 over gamma n, integral from 0 to infinity. I want to write this as a sum. So to write this as a sum, I should have 1 plus z e to the minus x, yeah. Well, technically I want this to be a minus, right? So it's going to be a minus. We'll see why in a second, but let me just write the denominator, right? Like this. This is actually minus n to the minus 1. But we should multiply the top by this, so that when we divide everything by, so when I bring this to the bottom, right, so let's say I bring this to the bottom, I get z to the minus 1 times e to the x. This cancels out and gives me a plus 1, and this gives me a z to the minus 1 e to the x, which is precisely what we have here. So this works. Okay, and the reason I do this is because now this 1 over 1 minus z to the minus x is expressible as the result of an infinite geometric sum. So integral from 0 to infinity of x to the n minus 1 z e to the minus x, sum from 0 to infinity of minus z e to the minus x, right? This to the power of m. Yes, okay. Now I bring out this sum, I bring in the integral, so 1 over gamma n, sum from m 0 to infinity of z times minus z to the power of m times integral from 0 to infinity of x to the n minus 1 e to the minus x e to the minus mx dx. Now this can become a minus, and I put a minus here, and this becomes minus z to the m plus 1. Fairly simple algebra for now. Now I want this again can become e to the minus m plus 1 x, right? And now I can do one last substitution. So I let u be equal to m plus 1 x. So du is equal to m plus 1 dx. So this integral, right, becomes x to the n minus 1, so 1 over no, first I want this integral to change, so this sum to change. So this is from m equal to 0 to infinity, but here I have m plus 1 and here I have m plus 1, so I might as well just do a sum from m equals 1 to infinity and get these m's to just be equal to, so get these m plus 1s to just be equal to m. So this is e to the minus mx, and now this integral, right, this integral is equal to, so this is m without the plus 1. So this is 1 over m to the power of n minus 1 times 1 over m from the dx, integral from 0 to infinity of x to the n minus u to the n minus 1 e to the minus u du. This is a gamma function, right? This is gamma of n by definition, so these cancel out, and in the end result, what do I find? I get this is equal to minus 1 over, no gamma function. This is equal to minus sum from 1 to infinity of minus z to the power of m over m to the n, and lo and behold, this is just minus gn of minus z. Okay, so we can get the Fermi-Dirac functions from the so-called from the Bose-Einstein functions. They are related like this. Okay. So we've looked at these functions. Why? Because they popped up when calculating the average number of bosons, right? So going back to that calculation, so going back to this, I recognize that this is equal to gs v over 4 pi squared 2m over h bar squared to the 3 halves. I'm not sure why I have an e here. It should be a beta, right? Yeah, it should be. So 1 over beta h bar squared integral from, sorry, and then I have just this Bose with this Fermi-Dirac function. So f of, well, what is n? N is the power here plus 1, so 2 of z. And actually I can write this in the following more f of 2z, yeah, plus times f gamma of 3 halves. Okay, so here we should have had a 1/2. So we can write this as g of s v over 4 pi squared 2m over beta h bar squared to the power of 3 halves, right? I brought this beta into this parentheses. Then I have this integral, right? But remember, I can now express these as Fermi-Dirac functions, right? This is equal to f of 3 halves, z gamma of 3 halves, and there's an expression for this gamma function which you can calculate, and at the end you can express this quite easily as gs v over the thermal wavelength cubed, which comes from this parentheses, times f of 3 halves z. Okay, so this is equal to, this is an expression for the number of particles. Now let's do the same. Let's do the same with the internal energy. So the internal energy, let me move here. So now the internal energy we said is equal to integral of GE E dE 1 over z to the minus 1 e to the beta e plus 1, and we said this is equal to gs v over 4 pi squared 2m over h bar squared to the 3 halves times integral of, and I got a beta here as well because of the change of variables, x to the power of 3 halves over z to the minus 1 e to the x plus 1 dx. Okay, there we go. And this goes from 0 to infinity. And this again, well, what is this equal to? This is equal to gamma of 5 halves f of 5/2 Z. And you can do the same thing of using the definition of the thermal wavelength, and the end result is that U is equal to 3 GS V over 2 beta times the thermal wavelength cubed f of 5/2 Z. Okay. Finally, let's look at the grand canonical potential. So PV, right? This we said was equal to the integral of GE log of 1 plus Z e to the minus beta E dE from 0 to infinity. And again, I can write this in a different way actually. So this time I'm going to get clever. I'm going to define the integral of GE, right? So this is equal to GE dE. And it's fairly easy to see that because this is proportional to e to the 1/2, this must be equal to 2/3, right? GE, right? This 2/3 comes from inverting 3/2, which comes from here when you add 1. Okay, plus some constants we don't really care about, because now this can be integrated by parts. This is equal to GE log of 1 plus Z e to the minus beta E from 0 to infinity. But remember, this integral this thing in brackets vanishes at both infinity and at 0. So this term can be neglected. In the density of states, it makes sense, right? That the density of states should vanish here in this limit, in the limit of 0 energy. And when energy goes to infinity, well, this gives me this gives me a 0, and the log of 1 is just 0. So it all hinges on this next integral, which is from 0 to infinity of GE time divided by Z to the minus 1 e to the beta E plus 1 dE, after some very simple algebra. And now we use this to write this as 2/3 integral from 0 to infinity E GE dE over Z to the minus 1 e to the beta E plus 1, and this integral by definition is equal to the internal energy. So 2/3 of U. Okay, so we found that PV is equal to 2/3 of U, and so we can use this and get this written as, well, it's nice because the fractions cancel out, GSV over 2 beta thermal wavelength cubed f of 5/2 Z. Nice. Okay, so there we go. These are the main quantities for the Fermi-Dirac distribution. We've pretty much calculated them to a good precision. I mean, we use the density of states, and that requires to be at fairly, you can use this at, say, absolute 0 or close to absolute 0. So we're going to have to develop different approximations if we're dealing with high temperature, low temperature, or 0 absolute temperature. And we'll look at these 3 different cases.